2 videos ago, we talked about polarity and how a bond can be polar when the electronegativity between the two atoms is different. So when we talked about, I believe, I think it was the HCl bond, and we said that since chlorine is more electronegative than hydrogen is, that there is this, again, what we call a dipole to the right, which we're going to talk about in more detail today. But if you have just the regular Cl2 bond, because both atoms have the same electronegativity, this bond is considered to be a nonpolar bond, where this bond up here, because it has a dipole, is polar. So just to kind of review of that real quickly, so if a bond is polar, it creates what's called a dipole. And if this molecule overall is polar, then we can say that it has what's called a dipole moment. Okay, a dipole moment, it's kind of like in an airplane. In an airplane, if there's more people, or there's more weight on the right-hand side than on the left-hand side, the airplane would tend to want to lean one way. Okay, and that means that the airplane has what's called a moment, okay, which means that it's unbalanced, okay? Same thing here. If something has a dipole moment, it means basically that the electrons in the bond are not balanced and they're more attracted to one side than to the other. So a dipole deals with the separation of those positive and negative charges. Here you can see it as well, that because fluorine is more electronegative than hydrogen is, again, we've got a dipole going in this direction, showing that the electrons are more attracted to the fluorine side than they are to the hydrogen side. Okay, and what that does, as you can see, this is basically means that's a slight charge. Okay, so you've got the slight, let me make that arrow. The slight positive charge over here on the hydrogen, and then again a slight negative charge over here on the fluorine. Okay. Now, what happens though when you have more than one bond? Okay, we looked at here, one bond, just one bond. What happens when you have 2 or 3 or 4 or 5 or many bonds? Okay, what happens is oxygen, for example, here's carbon dioxide, where oxygen is more electronegative than carbon. These are their electronegativities. So oxygen is more electronegative. So this kind of shows this, but basically, yes, you've got a dipole going this way, and you've got a dipole going this way. Okay, those dipoles are equal to each other. Okay, in that they're both pulling. It's kind of like a tug of war. If both sides in a tug of war are pulling with the exact same force, then what happens? Nothing. Okay, so since oxygen has the greater electronegativity, okay, that means there's a dipole to the right, there's also a dipole to the left. But because both of those dipoles are equal to each other and they're exactly opposite each other, what happens is, just like a tug of war, what happens in the tug of war when both sides are pulling with the same strength? They cancel each other out. Okay, so the dipoles cancel, and therefore, even though those bonds are polar, that this is a non-polar molecule because the dipoles are equal and opposite and they cancel each other out. So yes, CO2 contains 2 polar bonds, but because the dipoles cancel each other, overall it has a dipole moment of 0. And really what that means, it basically means it doesn't have a dipole moment. It has no dipole moment, which means it's even, right? It's even on both sides, so it cancels out. Okay, now water, on the other hand, let's kind of take a look at this one, which this is the correct shape. Water is a bent shape. We've already learned that. The bond angles are a little bit less than 109.5. Okay, which of those two atoms is more electronegative? Whenever I ask myself that, I always just look at the periodic table. Which one's closer to fluorine? Because I know fluorine's the most electronegative. So oxygen is much closer to fluorine than hydrogen is, which means if we're going to draw those dipoles, we're going to draw a dipole going this way, and we're going to draw a dipole going this way. Okay? And if we average those two out, what we have is we really have, and you could do it below the oxygen or above it, but basically, if you combine those two together, we have an overall dipole that is pointing up. Okay? So what is the direction of the overall dipole? It's right there. Okay? Now, Similar to carbon dioxide, water also contains two bonds that are polar. But because they are not equal and opposite, they are equal, but they're not opposite each other, they don't cancel each other out. And we are left with an overall dipole pointing up. So we would say that water does have a dipole moment. Okay, so when the dipoles don't cancel, we say that the molecule has a dipole moment, and molecules that have a dipole moment are polar. Okay, one of the great ways to think about this as well is to think about the word symmetry. Okay, in this case, CO2 is symmetrical. Okay, and when we say symmetrical, we mean that, again, the dipoles are going to cancel. In this case, with water, because you've got the lone pairs up here, okay, water is not symmetrical. And the way that you say that is you say that water is asymmetrical. Okay, you can say not symmetrical, but that is the correct way to say that. So a molecule that is symmetrical so symmetrical means that the dipoles cancel and is therefore nonpolar. If it's asymmetrical, it means that the dipoles don't cancel and therefore it is polar, and it does have an overall dipole moment. It means it's unbalanced, right? So how do you know? How do you know whether it's polar or it's nonpolar? The number one thing is you have to draw the Lewis electron dot diagram. Okay, when you draw the Lewis electron dot diagram, that will show you, is it symmetrical or is it asymmetrical? Okay, and there's two things that you're going to look for when you're trying to decide, is it symmetrical or not? Okay, if you take CH4, for example, CH4 is a tetrahedral shape, and all four of those bonds are equal in their electronegativity and their polarity, and therefore that is a non-polar molecule. That is a perfectly symmetrical molecule. But if I take, and this is what the first example is saying, if I take one of those hydrogens away and I make it a fluorine, well, now all of a sudden it's very, very unbalanced. That's like taking, two people on two opposite sides of the plane, and then taking one of those people away and replacing it with another person like me that's really, really big. Okay, and all of a sudden, in a small plane, all of a sudden that plane's going to start leaning more to the right. Okay, and so what that does is it throws off the symmetry. So CH3F, because of that, again, now that symmetry isn't there, that's asymmetrical, that is now a polar molecule. So anytime you take a nonpolar molecule and take an atom away and put another one in, that typically is going to turn it into a polar molecule. Okay, a more common scenario, though, is molecules that have lone pairs on the central atom are polar. Okay, so anytime you have, like the example here, NH3, okay, as soon as you see those lone pairs, you go, oh, polar. Okay, anytime the atom they're asking you about has dots on the central atom, it's polar. Okay, so example 1, NO2 minus. Is it polar or nonpolar? Explain. Okay, the first thing we have to do is we have to draw it. So NO2 minus, first of all, we're going to count the electrons. It has 18, 5 plus 12 plus 1 with that minus charge. So we're going to draw the Lewis electron dot diagram based on the way that we've learned it. There's 16 electrons. I have 2 left, so 17, 18. And now I'm going to take 2 electrons from one of the outer atoms and make that double bond. And that is our correct Lewis electron dot diagram. Okay, I could ask you about the shape of that molecule. You would tell me that it's bent. I could ask you about the bond angles. You would tell me that those bond angles are roughly a little bit less than 120 degrees. Okay, and now I can ask you, is this polar or non-polar? Okay, and the first thing you're going to do is you're going to tell me that it's polar. Okay, so it is polar. Now why? And I'm going to underline the things that I'm going to be looking for in answers. Because the lone pair of electrons on the central atom, okay, make the molecule asymmetrical. So the dipoles do not cancel out. Because even though I drew that linear, it's not linear. Remember that. Okay? And that's all I'm really looking for. It's asymmetrical. The lone pair makes it asymmetrical. If it's asymmetrical, that means the dipoles don't cancel, and therefore it's polar. Because what does NO2 really look like? It really looks like, remember, it's bent, so what does it really look like? It really looks like this. And oxygen is more electronegative than nitrogen, so you've got a dipole going this way, and you've got a dipole going this way. Okay, and so overall, what do you have? Combining those two, you really have a dipole pointing down. Those dipoles don't cancel each other out. NO2 is polar. Okay? All right, identify the following molecules as polar or nonpolar. I'm going to go through these quickly, but I just want to show you some more examples. So CBr4 looks like this. It has no dots on the carbon in the center. Each bromine has a single bond with 6 dots on it. That is a tetrahedral shape, bond angles of 109.5. Because there's no dots on the central atom, we haven't replaced any of the outer atoms with a different atom. That is absolutely a non-polar molecule. Okay, and how would you justify that if I were going to write that? I would say it's non-polar because CBr4 is symmetrical, and therefore all the dipoles cancel, and that makes it non-polar. Okay, so that's, again, symmetrical, and talking about how the dipoles cancel. That's again what we're looking for. Okay, NS2. NS2 has 5 plus 12 minus 1 is 16 electrons. So we're going to end up with this. Not oxygen. Oops. I was thinking it was CO2. With this molecule. Okay. And again, you can see that there's there are dipoles there. Now, in terms of which one's more electronegative, because nitrogen's farther up, but sulfur's farther to the right. Which one's more electronegative? I don't know, and I don't care. But I do know that those definitely are polar bonds. But let's say that sulfur's more electronegative. Then you've got a dipole going this way and a dipole going this way. It doesn't really matter. It is a linear molecule. They do cancel each other out. Therefore, non-polar. Okay. PF3 looks like this. It is a trigonal pyramidal shape. Bond angles of a little bit less than 109.5. Okay, you've got that lone pair on that central atom. Therefore, it is polar. And why? Because it's asymmetrical. Why is it asymmetrical? Asymmetrical because of the lone pairs. Not lone pairs, the lone pair of electrons on that central atom, and therefore the dipoles don't cancel. Okay, polar. Okay, CH2O, the C goes in the middle, the other atoms go around C. So you've got a C, H, H, double bond to the O, looks like that. That is a trigonal planar shape. If all three of those bonds were the same, then you would have a dipole going this way, and this way, and yes, all three of them would cancel. Okay? If it's linear, if it's trigonal planar, or tetrahedral, those dipoles will cancel if all of the outer atoms are the same. But because oxygen is more electronegative, you've got a much, much bigger, I'm making it bigger by making that dipole more filled in. Much more of a dipole pointing up than you do having pointing down into the sides. Okay, and this is one where we've replaced one of the outer atoms with a different atom, therefore it is polar. Why is it polar? It's asymmetrical, and it's not asymmetrical because of the lone pair, it's asymmetrical because oxygen is more electronegative than hydrogen. Okay, and that's it for polarity. Good job.